Hi, and welcome to this next video where we continue our discussion of learning theory. In particular, this video is part of a sequence of 4 videos where we start by looking at testing, then overfitting, regularization, and validation, which are key techniques in machine learning. So again, this one video here is about testing. So let's try to explain and motivate testing. Okay, so if you recall what happened in the previous video, we introduced this notion of VC dimension. And basically, we showed that if you have a bound on the VC dimension of the hypothesis set that you're using to find a good hypothesis for your data, then you could give these guarantees that say, well, basically the probability over a set of n training examples that the hypothesis H star that your machine learning algorithm outputs, the chance that the in-sample error of this hypothesis, the performance on the training data, differs from the outer sample error, so the chance of making a mistake on a new data point, the chance that these are more than epsilon apart is no more than this expression here on the right, which has a term here which is like 2n to the VC dimension, and it has an expression that's e to the minus epsilon squared and up to constant factors. So this is basically a formula for arguing that you can trust that the in-sample error is a good estimate of the outer sample error as long as you have enough data. Right, and this formula here really gave us some insights just by looking at it. In particular, we can see based on this formula, that if the more data I have, the performance on the training data is a better and better predictor of the true performance of this model that I trained on new data. Also, the more complicated hypothesis that I use, then on the other hand means that they get further and further apart, or you cannot really trust necessarily that that these are close. Okay, so you have this kind of trade-off that the more complicated model you use, the easier it is also to get a small in-sample error, but then it's not certain that the outer sample error is also small. And finally, right, so we also argued before that minimizing the in-sample error as a general strategy for training a machine learning model is a good strategy as long as you have enough training data. Okay. So in addition to giving us these insights, you could also try to use this VC bound in applications as the following, right? So let's say that you have a customer that asks you to train a machine learning model. And so you do this, and the customer would like to know, because they're using it in an application, right? They would like to have an estimate of how good is this model that you trained actually on new data. Right. So perhaps they know a bit about the theory of machine learning, and they say, okay, I'd like to have an estimate of the outer sample error of this model, and it should be accurate to within 0.1, so 10%, with 90% confidence. Right. So then you could ask yourself, okay, so how much training data would I need in order to guarantee this? And basically what I have available, right, if I have some training data, I can compute what is the in-sample error, and I know that the hypothesis that I use, perhaps I have a bound on the VC dimension. Maybe I know that this hypothesis set has VC dimension 25. Then I could use this bound that I computed to give such a guarantee to the customer, right? So basically, if I have this bound, I can just try and plug in these numbers and figure out how large an n do I need in order to obtain this guarantee. So let's try to do that just to see how these different numbers here fit into the formula. So, right, so what we said was that the VC dimension was 25. And what we also said is that we would like an estimate that's accurate to within 10%, which means, and we could compute the in-sample error, right? We know the in-sample error. So we can say, okay, if I want an estimate of the outer sample error that's accurate to within 10%, then I need this epsilon to be 10%. And I would like that this estimate is within these 10% with 90% probability, which translates into the chance that the further apart than 10% should be at most 10%, right? So this means that I would like that the right-hand side of this expression should be at most 0.1, because that gives this is the confidence, right? Now, this is the chance that you're outside the confidence interval. So really, I have an epsilon of 0.1, I have a d of 25, and I want this right-hand side to be less than or equal to 0.1. So now I just need to solve this for n. So I have enough data if this right-hand side here is no more than 0.1. That's what we just said. So let's just try and plug in the numbers, right? So we said d to be 25. We said epsilon to be 0.1. So 0.1 squared, that's 1 over 100. So up here in the exponent, we get n over 800. Okay, so this expression here is like it's not really one that is easy to get a closed form solution to. So what we could do is we can just try some guesses for n and see if we can get a good estimate. Okay, so maybe we can start by trying a wild guess of maybe 8,000 training examples are sufficient. So if we plug in 8,000 in place of n, down here, the two n terms in here becomes 16,000 raised to the 25. The expression here with e to the n over 800, that becomes e to the minus 10. And we want all of this to be less than 0.1. If you use a calculator, you'll see that 16,000 to the 25, that's about e to the 242. It's a little bit less than that, but very close to. It's like e to the 241 point something. So really, you essentially need this whole expression here to be less than 0.1. And clearly it isn't, right? You have an e to the 242, but you only have an e to the minus 10 to kill it. So this is definitely not enough samples. Okay, so let's try a bigger guess, right? Let's plug in 80,000 instead. So if you plug in 80,000 instead, right? Instead of 16,000 here, you get 160,000 raised to the 25. Instead of e to the minus 10, you get e to the minus 100. But if you plug in the numbers here, and you'll see that this is roughly e to the 300. So still, this is not enough data, right? Because we only have an e to the minus 100 to kill an e to the 300. So let's try an even bigger guess. So let's try a 400,000 training examples. So if we plug in 400,000 training examples, and down here we get 800,000 to the 25, and here we get e to the minus 500. Now, here we're finally getting somewhere, because if we plug in these numbers, you get something like e to the 340, and we have an e to the minus 500. So now actually 400,000 training examples are enough, 80,000 isn't. So the VC bound, if we use it to give this guarantee to a customer, say the customer wants an estimate that's accurate to within 10% with 90% confidence, we're using a hypothesis set of VC dimension 25, then the VC bound says that we need somewhere between 80,000 and 400,000 training examples, which actually sounds like quite a lot, right? This is really a lot of data that you need to gather. And it turns out that in practice, this is a very pessimistic estimate. And the thing is, in general, this VC bound just turns out to be very far off in practice. Okay, so actually a good rule of thumb is that sometimes this is like maybe around a factor 1,000 off in terms of the number of data items that you need. Okay, so this is really unfortunate, right? A factor 1,000 in terms of the number of data items. This is really something that you really cannot live with if you want to give guarantees to a customer. Then, of course, you could ask yourself, what is the reason why this VC bound is so far off in practice? Maybe the first question you could ask, as the theoretical question is this even the right asymptotic behavior, right? So is this formula over here, even if we ignore the constant factors, does it even grow in the right way? And actually, it turns out that no, it's not a wrong formula. There are actually examples of data distributions and hypothesis sets where this is right asymptotically, right? So if you ignore the constant factors, this is the right formula, at least for there are data distributions where it's the right formula. Okay, no, so what really happens here is that oftentimes in practice, real data is just easier than worst case data, right? Real data is not what gives the worst case bound for the VC dimension generalization bound up here. And also, right, the constant factors in this expression, maybe they're not the right ones, right? Maybe this 8 in the exponent, right? If you could replace it by 1, you'd already have gained a factor 8 in the amount of data and so on, right? So you can easily imagine that some of these constants are off. And also just this fact that data in real life is not worst case. So in general, there's some good rules of thumb that says that, okay, if you want the guarantee that the outer sample error is no more than 10% bigger than the in sample error with 90% confidence, then you need maybe something like 10 times the VC dimension data. Right, so this is much less. So at least for this data example that we had before with, if we said that we have VC dimension 25, this says that we need something like 250 data items. 250 data items compared to this pessimistic bound of between 80,000 and 400,000 samples, right? You can even see that 250,000 lies in that interval. So this is this factor 1,000 in terms of the estimates that we talked about. So something like 250 data items would typically be enough for this kind of guarantee. But this is just a rule of thumb, right? It's not a theoretical proof of anything. So if the VC bound is so far off in terms of the constant factors that you can't really use it to give any guarantees of this type, what good is it, right? What could we use it for? And I think, at least to me, like the main reason, intuition from it is that we learned something about the effect of using a complicated hypothesis set, right? And maybe also the asymptotic behavior is still the right kind of dependency on, maybe the dependency on this epsilon you want is a quadratic dependency on epsilon, and the dependency on the number of training example is an exponential dependency, So you can still get all these intuitions out of the bound, even though you cannot use it to get concrete numbers when you want a guarantee like this. Okay, so let's say I still would like to solve this problem here where I have this customer, I'd like to train a model for them, and I would like to, along with the model, to give a good estimate of the outer sample error with good confidence. So then you could ask yourself, what other things could you try and do? And here testing is a technique for exactly this purpose. So what you can do is you can say, well, before you start, you take some of your training data that you gathered and put it aside and call it a test set. And so you kind of just take some of the data and put it aside. And then you train on the data that you have left, right? So you just ignore the data that you set aside as a test set. So you train on the remaining data. And then what you do is you will use this test set to estimate the outer sample error. Okay, so let's go into more detail about this, how this exactly works. So in general, right, here's the full data set that I have. I have a lot of data that I've gathered. I know all the labels. So I take some of this data set and set it aside as the test set. So I move them over here. And now what I do is I train on my remaining training data. And from this, I find a hypothesis H star, right? Maybe if it's a linear model, maybe I find one here that actually perfectly classifies the training data. Now what I do is I take that hypothesis and then I compute its accuracy on the test data set, right? So you can see here, if you go back to the original training data, this hypothesis here would classify blue to everything above the line and red to everything below the line. So if you do that over here, blue to everything above, you'll misclassify this one example here, and red to everything below, you'll misclassify one of the examples down there, right? So you're misclassifying 2 points out of the 6 points that you have available, which means that the test error is a third, right? You're misclassifying a third of the data. Okay. So what we say is that the estimate that we're going to give to our customers is basically going to be this test error, right? So we're going to claim that this test error is a good estimate of the outer sample error. Okay. So now, of course, we can ask ourselves, this test error that we return here, how accurate is it actually? Is this a good estimate of the outer sample error? Let's try to see it. So can we give here, like we did with the VC bound, can we actually give theoretical guarantees on how accurate an estimate the test error is of the outer sample error? So let's try to see. So maybe we could try somehow to use the Hoeffding bound here, like that we saw earlier, right? So what did the Hoeffding bound said, right? The Hoeffding bound, if you remember many videos ago, was this case where we looked at, let's say I have just one hypothesis H. My hypothesis that is just a single fixed hypothesis. Then the Hoeffding bound said that, okay, if I draw a training data set of n examples, then the chance that for this one fixed hypothesis that the in-sample error and outer-sample error are further apart than epsilon is no more than 2 times e to the minus 2 epsilon squared n. Okay, so then you can ask yourself, what are the assumptions that went into this Hoeffding bound? What do you need, right? And what you need is that this hypothesis H, it's like a fixed one that is not dependent on the n training examples that you evaluated its in-sample error on. Okay, so basically the setup was the following, right? That somehow we should assume that these n samples that you compute the in-sample error on, they should be generated as independent samples from the same distribution D. Which means that basically, if I have a fixed hypothesis that doesn't depend on them, then you can think of the in-sample error is essentially the same as flipping n coins. And each time you flip a coin, you basically flip a coin that says, if it comes out heads, this means that I accidentally got one of the training samples, or one of the samples that you misclassify. And which means that since we come as independent samples from the distribution D, the chance of getting one of those samples, the probability of a heads, is exactly the outer sample error. And the in-sample error then of the hypothesis is exactly the fraction of heads that you see in your training data. Okay. So the Hoeffding bound basically said that if I have this experiment where I toss n independent coins with the same probability of a heads being the outer sample error, then the chance that this in-sample error and outer sample error are more than epsilon apart is no more than this 2 times e to the minus 2 epsilon squared n. Okay. So this is what we said when we just had a single fixed hypothesis. Then we could use this Hoeffding bound. So the question is, can we somehow use this Hoeffding bound also for this test error here? Like, is this a similar experiment that's happening? So let's try to see. So when we're in this testing setup, right, what we could do is we say, okay, so we have this test set that we choose in advance, right? And there's several ways we could choose it, right? But if we choose the test set without actually looking at the data, so if we say, okay, my test set is just a random subset of k items, or maybe it's the first k items, so I don't look at what the data items actually are. I just pick them somehow without looking at it. So the first k or a random set of k items. That's good choices. In practice, you would choose a random set of k items. So if I choose a random set of k items as my test set, then what you have is, at least by this assumption, the data is independent samples from an unknown distribution D, then the remaining n minus k training examples are independent samples from the distribution D, and the k test items are also independent samples from the distribution D. And in particular, they don't depend on the n minus k remaining training examples. So what this means is that if I train a hypothesis H star without looking at the test set, the k items I chose as my test set, then you can still use the Hoeffding bound because the hypothesis set is chosen independently of these k training examples. Right? They are drawn as independent samples from the distribution D, samples that don't depend on the hypothesis H star. So this basically means that if I have a test set of size k, then if my hypothesis, the one that my learning algorithm returns, doesn't depend on the test set, then basically when I get the test set, I can think of it as this test set, basically flipping k coins. And each time I flip a coin, the probability that I see ahead is exactly the outer sample error of H star. And then the test error is the fraction of heads that I see, right? Which basically means you can think of it as the test set is kind of being generated after choosing the hypothesis. And each of the each of the test examples, since they come from the distribution D, all of them will be misclassified by H star exactly with probability equal to the outer sample error of H star. Which means we can use Hoeffding's inequality and we can show that the probability that the test error of the hypothesis learned by the algorithm on the training data, the chance that this one is further away from the true outer sample error of that hypothesis, the chance that they're further apart than epsilon is no more than what the Hoeffding bound gives us, 2 times e to the minus 2 epsilon squared k now. So k is the size of the test set, right? And those are the ones that we have here. So the intuition one should have in mind is really, you kind of use the training data to find a hypothesis H star. And then in some sense, you can think of, oh, now I have a fixed H star. And now my test set is drawn afterwards. So I kind of get a new test set, and this test set is drawn independently of H star. So I kind of think of it as there's a fixed H star, and the test set is just drawing independent samples. And so the performance of H star on the test set is going to be very close to the performance of H star on new data. So really, if we want to compare the type of guarantees that we have so far, now, what we just saw is that the probability that the test error and the outer sample error are more than epsilon apart is no more than 2 times e to the minus 2 epsilon squared k. In previous videos, we also looked at, well, if I have a finite set of hypotheses, if I have m of them, capital M of them, then we showed these bounds that the chance that the in-sample error, not the test error, but the in-sample error of H star, being the hypothesis that learning algorithm finds, and the outer sample error, the chance that they are more than epsilon apart is no more than 2 times m times this e to the minus 2 epsilon squared n. So here you gain the number of different hypotheses is a multiplicative factor onto this expression that we have here for the test error. Though on the other hand, what we gain is that we now have an n up here. We have the full training data available, where up here we only have the k test elements available. And finally, right, we have if you had an infinite hypothesis set and you have a bound on the VC dimension, then we get these other guarantees like the one we have here, right? Now, the nice thing about the test error up here is that this also works for infinite hypothesis sets, and there's not even a dependency on the complexity of the hypothesis set, right? It only depends on the performance of the test set, right? So really what you see here is like the testing is much more accurate, because basically the only thing that you're testing is the actual hypothesis that you're going to return. Whereas if you think about the proofs that if we went through for the other two bounds, right, what they actually do, they're actually very pessimistic. What they do is really they say that not just the hypothesis, it's not just the hypothesis that the learning algorithm returns where the in-sample error and out-of-sample error are within epsilon. It's actually all possible hypotheses in the entire hypothesis set where the in-sample error and out-of-sample error are within epsilon. So it's a much stronger guarantee to ask for. So somehow it also, the estimate that you can get out of this example are really like a worst case guarantee that even if the learning algorithm somehow picked the hypothesis with the very worst gap between sample and out-of-sample error, then this guarantee that we give still holds. So that's really because of this union bound in the bounds. So one should think of the two bounds that we have at the bottom here. They're really pessimistic. They kind of hold for any hypotheses that the learning algorithm could produce. You would get this guarantee. Whereas the one that you have up here with the test set, the guarantee is only on the single hypotheses that you're actually going to return by your learning algorithm. The downside, of course, is that you have less data for training because you have to set aside these k items. So it's really a balance between k and n, right? And if you want to give a customer a guarantee, you have to ignore some of the data, which is of course is worse for training, right? So if you have less data for training, maybe the model that you find is not the best one, and so on, right? The more data you have, the better the strategy of minimizing the in-sample error typically is. Okay, so that's the downside. So let us just conclude by something that's a bit related to all the things we've seen so far about in-sample error and out-of-sample error and model complexity. So what I'll just show here is what we call the learning curve in general. So it's really a plot of the two situations of what happens when you have simple models, so simple hypothesis sets, and more complicated hypothesis sets. So the general idea is that if I have a simple model, right, and then the issue with a simple model is that, well, it cannot really give a good in-sample error, right? And typically, if I have more and more data, right, it's harder and harder to get a good in-sample error because I have more data that I need to fit. And if the model is very simple, then somehow it just cannot, there's not a hypothesis that is super great on the in-sample error. Now, the good thing about it is really that if you have a simple model, then the in-sample error and out-of-sample error are going to be close, even for very little data, right? So the gap between the in-sample error and out-of-sample error is small. On the other hand, if I use a really complicated model, then I can actually get a really good in-sample error. In particular, if I have very little data, then I can perfectly fit it. And in general, right, I can drive the in-sample error much further down. But on the other hand, right, the issue is that the gap between the in-sample error and out-of-sample error is much bigger. So I need much more data before the in-sample error and out-of-sample error get close. If you compare these two plots again, what you'll see is that, if I don't have that much data, then over here in the beginning, the in-sample error of the simple, and also the out-of-sample error of the simple model is actually less than it is for the complicated model, right? If I don't have that much data. When I begin to have more and more data, then simply because I can drive the in-sample error further down, if I have enough data, then the out-of-sample error will go down with it, and I can get a better performance with a more complicated model than with a simple model. But the trick is that really you need more data to justify using a more complicated model. Okay, so let's end this video on that remark.